Hello students, welcome to Lucky Learning. Here in this video, I am going to discuss RISC pipeline. What is RISC? Reduced Instruction Set Computer Pipeline. The major characteristics of RISC processor are the relatively it uses fewer number of instructions, lesser number of instructions, and lesser number of addressing modes, and memory access limited to load and store instructions. It means load from the memory and store into the memory. And all operations done within the CPU registers. But when in the case of RISC processor, the operations can be done directly on the memory. But here operations can be done within the CPU registers. And instructions are of fixed length. Because it is fixed length instructions, it can be decoded easily. And it uses single cycle instruction execution, means within one cycle it is going to be executed, means in single clock cycle the instruction execution is possible. And it is called hardwired rather than microprogrammed control, means it is considered as hardwired control instead of microprogrammed control. The reduced instruction set computer has ability to use an instruction pipeline efficiently. The simplicity of this instruction set is utilized to implement an instruction pipeline using small number of sub-operations, with each being executed in single clock cycle. In one clock cycle, the instruction is going to be executed. Because of the fixed length instruction format, the decoding of the operations can occur at the same time as the register selections are done. So that register selection and decoding can be happened at the same time. Since all operations are performed in the registers, there is no need of effective address calculation. Effective address calculation is required when the operation is going to be performed on the memory. But here operations are performed in the registers. There is no need of calculating the effective address. Therefore, the instruction pipeline can be implemented with 2 or 3 segments. When in the case of the instruction pipeline, it uses 4 or 6 segments. But in the case of RISC pipeline, it doesn't require 4 to 6 segments of pipeline. It uses only 2 or 3 segments of pipeline is sufficient. And to prevent conflicts between the memory access to fetch an instruction, to load or store an operand, most RISC machines use 2 separate buses with 2 memories, one for storing the instructions, other for storing the data. It is the problem in the instruction pipeline called resource conflict. Resource conflict occurs when one instruction wants to fetch, another instruction wants to fetch an operand from the memory. Then in such cases, it is going to cause a conflict called resource conflict, because one instruction is to be fetched from the memory, another instruction is to fetch a data from the memory. Both instruction wants to access the memory at the same time. That is a resource conflict. To avoid the resource conflict, we have 2 memories. One memory is for storing instruction, another memory for storing the data. So that one bus is connected to a memory that has instructions. So any instruction that is to be fetched, that can fetch from the instruction memory, and another bus is connecting to the memory that has a data. So any other instruction that requires the data at the same time is going to connect to that memory in the data, and the data is going to be fetched from the memory. And one of the major advantage of RISC is its ability to execute the instruction at the rate of 1 per clock cycle. 1 per clock cycle, an instruction is going to be executed. And moreover, the RISC is going to take the help of compiler. That is another characteristic of RISC is the support given by the compiler. And what is compiler? Which is going to translate high-level language program to machine language. Instead of designing a hardware to handle the difficulties, what are the difficulties that we have discussed in the instruction pipeline? Resource conflicts, data dependencies, branch difficulties. So we used hardware solutions. Means instead of designing hardware to handle the difficulties associated with data conflicts and branch difficulties or branch penalties, RISC processor rely on the efficiency of the compiler. Means it is going to take the help of compiler to detect those conflicts and minimize those delays that are encountered in the pipeline. Here we are going to use three segment RISC instruction pipeline. The three segments are instruction fetch, ALU operation, and execute the instruction. IAE. This IAE is going to be happen with different type of instructions that are going to be executed. What are the different types of instructions? We have data manipulation instructions, data transfer instructions, and program control instructions. And data manipulation instructions consisting of arithmetic, logic, and shift operations. In that, I segment uses instruction fetch. A segment is going to decode what is that instruction and read the register values and perform the particular ALU operation, that is arithmetic or logic or shift operation. And E segment is going to write the result to a register. When in the case of data transfer instruction, the I segment is going to fetch an instruction. A segment is going to decode the instruction and evaluate the effective address so that it is going to be perform a data transfer to memory or from memory. And E segment is going to perform the execution, that is transfer of data from register to memory or memory to register. When in the case of program control instructions, those are called branch instructions. I segment is going to fetch the instruction, A segment is going to decode the instructions and evaluate the branch address. And finally, E segment is going to write that branch address to the program counter, that is the next instruction to be executed is always in the PC. And these are IAE segments with reference to data manipulation, data transfer, and branch instructions. Now, when we see as a summary, in I segment, instruction fetch is common in all types of instructions. Now, we'll see what is going to happen in the I segment. The I segment is going to fetch the instruction from the program memory. And when it comes to the A segment is called ALU operation, is performed in the A segment. The ALU is used for three different functions depending on what type of instructions. It performs an operation for data manipulation instructions and evaluating the effective address in the case of load or store instructions. We also call data transfer instructions, and calculating the branch address in the case of program control instructions. And E segment directs the output of the ALU to one of the three destinations depending on the decoded instructions. It transfers the result of ALU operation into the destination register in the case of data manipulation instructions. It transfers the effective address to a data memory or for loading or storing in the case of data transfer instructions, and transfers the branch address to program counter in the case of branch instructions. Now we'll see how compiler will help you in the RISC pipeline. And we have seen the three conflicts. Those are called resource conflicts, data dependencies, and branch difficulties. And resource conflicts are resolved by having a separate memory for program instructions and data. Now we'll see how the branch difficulties and data dependencies are going to be resolved. Now first we'll see the data dependencies. The data dependency is going to be resolved by using the delayed load. For explaining this, I'll be using one example, the program, that is four instructions having load R1, which is going to store the memory value into some register R1, and second instruction is load the memory value into register 2, and third instruction is adding the two register values and storing into R3, and fourth instruction is storing R3 value into the memory at some location. If the three segment pipeline proceeds without any interruptions, there will be a data conflict. In instruction number 3, because the operand in R2 is not yet available in the A segment. So maybe you haven't understood this point. You can understand this point. This can be seen from the timing of the pipeline shown in the figure. Here you can look. What is the first instruction? First instruction is load R1. In the first clock cycle, it entered into the I segment. In the second clock cycle, the first instruction enters into the A segment and second instruction enters into the I segment. And in the third clock cycle, first instruction is executed so that the value of that memory location is going to be stored into this R1 register. This R1 register contains a value at the end of clock cycle 3. At the end of clock cycle 3, assuming memory at some address having value 5, that 5 is loaded into R1. And the second instruction entered into ALU operation, and in the third instruction is going to enter into the I segment. In the fourth clock cycle, the second instruction is going to be entered into the E segment. It means memory at some location, it has some value 6 that is going to load into R2 register. This is going to happen at the end of the fourth clock cycle. At the end of the fourth clock cycle, the R2 is going to be stored with 6. And in the fourth clock cycle, the third instruction is going to enter into the ALU operation. What is the third instruction? The third instruction is going to perform addition of R1 value and R2 value. R1 value is available at fourth clock cycle because at the end of third clock cycle, R1 already had a value 5. But R2 value, that is 6, is available at the end of the fourth clock cycle, but during the fourth clock cycle only it is going to perform R1 plus R2 because the third instruction entered into the A segment. It means the value of R2 that is not available at the fourth clock cycle, but the third instruction wants to perform the ALU operation, that is addition of R1 plus R2. It means at the end of third clock cycle, R2 may have some garbage value and R2 has 6 only at the end of fourth clock cycle, but during the fourth clock cycle only it is going to perform the R1 plus R2, that is 5 plus some garbage value that is going to be executed and will give you the incorrect results. This is called the data dependencies, the second and third, because third instruction requires a data which is the result of the second instruction and that is not yet available. This is called data dependencies. And in the fourth clock cycle, the fourth instruction is going to enter into the I segment. And in the fifth clock cycle, third instruction entered into E segment, fourth instruction entered into A segment. But in the sixth clock cycle, fourth instruction entered into E segment. But what happened here? The result of these four instructions results in a incorrect results because it had a problem of data dependencies. How this is going to be resolved? By delaying the load. It means this third instruction cannot be executed immediately after the second. Between the second and third, if we insert some instruction which does not have any meaning with that, so that it is going to delay the load operation. This is called delaying the load. To do this, RISC uses compiler support. So compiler is going to identify these difficulties and going to insert that no operations instructions between the second and third. How? We will see. Right? Here, compiler adds what? No operation instructions. Where to add? Between second and third instructions. Look at in the first clock cycle, that instruction 1 entered into the I segment. In the second clock cycle, instruction 1 entered into A segment and instruction 2 entered into I segment. In the third clock cycle, instruction 1 entered into E segment, instruction 2 entered into A segment, and third instruction is a no operation which is inserted by the compiler, that is entered into I segment. In the fourth clock cycle, load R2 is happen So means R1 is having the value 5, which is loaded from the memory at the end of third clock cycle, and R2 is going to have the value 6, which is loaded from the memory, assuming 6, and that is available at the end of fourth clock cycle. And in the fourth clock cycle, the fourth instruction is entered, that is add R1 plus R2 entered into I segment. In the fifth clock cycle, no operation is executed, and fourth instruction entered into A segment. Now, previously, what happened? This E segment and A segment happens at the same clock cycle. It results in incorrect results because no operation is inserted. It requires to perform the value of R1, that is 5, plus the value of R2 because R2 already have a value 6 because it is available at the end of the fourth clock cycle. Now R1 plus R2 is going to happen at the fifth clock cycle. So that 5 plus 6, 11 is going to be possible. Addition of R1 plus R2 is possible. There is no dependencies. This is resolved by adding no operation instructions. So that pipeline will continue. And this is how compiler is going to resolve the data dependencies by inserting no operation instructions. If the compiler cannot find any useful instructions to put after the load, it inserts a no operation instructions. This type of instruction that is fetched from the memory but has no operation to do it, thus wasting a clock cycle. This concept of delaying the use of the data loaded from memory is referred to as delayed load. And here, the advantage of the delayed load approach is that the data dependency is taken care by whom? Compiler, rather than the hardware. So in the instruction pipeline, we have discussed about how this is resolved by using the hardware. But in the case of RISC pipeline, it is taking the help of compiler. So compiler will take care of this data dependencies. Now, we will discuss about the branch difficulties, how by delaying the branches. For this, I'm assuming some example which has some set of instructions 1, 2, 3, 4, and 5. That is load from memory to R1. So R1 is loaded with some memory word and increment R2. R2 is incremented and add R3 to R4. R3 and R4 is added. Result is stored into R3 and subtract R5 from R6. R6 minus R5 result is stored into R5 and branch to address X means address X is copied into PC. So these are the 5 instructions. Now the method used in the RISC processor is to rely on the compiler as we know it to redefine the branches so that they take effect at the proper time in the pipeline. This method is referred to as delayed branch. And for delaying the branches, there are two ways compiler can solve this. One is by inserting the no operation instructions, and another one is reordering the program instructions. How? We will see. In the first clock cycle, load R1 is happened, and in the second clock cycle, increment. And in the fourth clock cycle, second instruction is executed, and third instruction is entered into the A segment, and fourth instruction is entered into the I segment. In the fifth clock cycle, third instruction is entered into E segment, and fourth instruction entered into A segment. And in the sixth clock cycle, the fourth instruction entered into E segment, and fifth instruction is entered into A segment, right? Fifth instruction is entered into A segment, that is a branch to X. So means branch to, assuming 12th instruction, it has to branch. So when when the control should transfer to 12th instruction at the end of this execution. At the end of this execution, it has to be transferred the control to 12th instruction. Means after the execution of 5th instruction, it has to go to the 12th instruction. But because it is not ended, means that 5th instruction is not completed that execute phase. Means it is not entered into the E segment. So if no operations are not included, 6th instruction is going to be entered into the I segment. that should not happen because it is a branch instruction. To avoid it, it requires to insert no operations. Now, the fifth instruction entered into the E segment so that at the end of seventh clock cycle, that branch address 12 is going to copy it into PC when at the end of the seventh clock cycle. So that sixth operation entered into A. So means the 12th instruction should start in the 8th clock cycle, not in the seventh clock cycle. That's why in the seventh clock cycle also it has to insert one more no operation, and one more no operation is executed, and in the 8th clock cycle the instruction in the xth location, that is a 12th instruction, going into enter into the ith segment. Now here you observe it is space time diagram. In the space time diagram, for execution of these 6 instructions, it uses 10 clock cycles. It is wasting the number of clock cycles by inserting no operation instructions. And there is another solution is to reorder the instructions. The program is going to be rearranged by placing the add and subtract instructions after the branch instructions. Why? Because those can be happened because in the previously we have inserted two no operation instructions. Instead of these two no operation instructions, the fifth instruction will be placed between second and third instructions. So at the end of the fifth instruction, by the end of the fifth instruction, because third and fourth are can be possible to be completed. This is called rearrangement. Who is going to take care of this rearrangement? Compiler is going to take care of this rearrangement. Now you look at in the first clock cycle, load entered into I segment. In the second clock cycle, it entered into A segment, and the second instruction entered into I segment. In the third clock cycle, first instruction entered into E segment, second instruction entered into A segment, and that fifth instruction now comes into the third position so that it is entered into I segment, and the fourth instruction entered into E segment, third instruction entered into A segment, and the third instruction previously we have add, and that entered into the I segment. And in the end of the fifth instruction, that branch X, assuming the branch to 12th instruction, that 12th instruction address is stored into PC. It is happened at the end of the fifth clock cycle. So means the 12th instruction is going to be started at the sixth clock cycle, right? The 12th instruction is going to be started at the sixth clock cycle, right? Now look at, so by the time that fourth and fifth can be completed, means that is actually speaking, that is third and fourth instruction is going to be executed uh, by the end of the sixth clock cycle. Now look at, now fourth instruction entered into A segment, fifth instruction subtract entered into ith segment, and in the sixth clock cycle, fourth instruction entered into E segment, fifth instruction is entered into A segment. And what is it? Because branch 12 is there, because branch address is available at the end of the fifth clock cycle. At the sixth clock cycle, the instruction in the 12th position is going to be fetched. Now look at, it is fetched. So that in the seventh clock cycle, the fifth instruction is entered into E segment, sixth instruction entered into A segment, and eighth instruction entered into E segment. Sorry, in the eighth clock cycle, sixth instruction entered into E segment. So that the execution of all these 6 instructions completed in 8 clock cycle. Previously, it took 10 clock cycles. So how this is happened? By rearrangement of the program instructions so that the number of clock cycles are reduced, program execution becomes increased. This is the technique in compiler is called optimization. That's why RISC pipeline will take the help of compiler support, right? This is how RISC is going to resolve the resource conflicts, data dependencies, branch difficulties by taking the help of compilers. This is all about RISC pipeline. Hope you have understood. If you like the video, please share with your friends. Thank you.